Good day and welcome back for part 2 of the discussion on volumes. As a reminder, in our previous video, we discussed how we can go about finding the volume of some solid sitting above the x-axis from A to B. And the formula that we developed is it's the definite integral from A to B of what we refer to as A of x. And remember what A of x represents. It's the cross-sectional area of the solid at a value x. That is to say, if we're at the value x, and I imagine this solid to be a loaf of bread and I slice it with a knife, what's going to happen is we expose the cross-section corresponding to that value of x. And the area of that cross-section is represented by the function a of x. So let's go ahead and explore a common example. Let's set up an integral that represents the volume of the solid obtained by rotating the region bounded by the curves y equals x and y equals square root x about the line y equals 1. So the first thing to do with any of these examples is to sketch a picture. In fact, we will sketch a few pictures. Not only do we want to sketch the region enclosed, but we also want to sketch a rough approximation of the solid itself along with a washer that we are going to be dealing with. In this case, the region is enclosed by the curves y equals the square root of x and the line y equals x. So we can very clearly see kind of this sliver of area enclosed between the two curves. And in fact, I'm going to erase some of this extraneous work to just get it out of the way. And what we would like to do is form a solid by revolving this around the line y equals 1. So if we come to y equals 1, and note that's going to correspond to this point of intersection, we would like to form a solid of revolution by rotating about that line. And note the point of intersection by inspection is 1, 1. So let's see if we can give a rough sketch as to what this should look like. So we'll let y equals 1 represent this dashed line. And we're taking this region from above, this kind of crescent-shaped region, and we are rotating it about that line. So I'm first going to take the mirror image of it about the line, and then I'm just going to simply add some depth to it, show that we are rotating this about. And we can certainly write down a definite integral that's going to represent the volume of this solid. Note our x values are varying from 0 to 1, and what we need to be integrating in this case is a of x. And recall, we determine a of x by thinking of a value between 0 and 1, and what would the cross-section look like for this value of x. Now, note intuitively how we get this cross-section is we look at our region, and we think about this thin vertical line segment sitting above x. Rotating this line segment about the line y equals 1 would trace out that cross-section. So roughly, it would look something like this. It's an annular region determined by rotating this small line segment about y equals 1. So let's draw this separately and see if we can determine its area. So a of x will be the area of this, what we would refer to as an annular region. It's a outside larger circle with a smaller circle removed. And now you can maybe see why we previously referred to this as being a washer, as typically we will see a picture that looks something like this. So in order to write down its area, note we need to determine two things. Associated with this washer there is a larger outside radius, which I will call big R, and a smaller inside radius I will call little r. And in general, the area of this washer, and I'll put this to the side, it would be the area of the larger circle, pi r squared, minus the area of the smaller circle, pi times little r squared. And in our picture, we need to determine what is going to play the role of little r and what is going to play the role of big R. And note we can see this almost by inspection. Little r is the distance this closer curve is away from the line that we are rotating about. Big R is the distance that further curve is away from the line that we are rotating about. So in our case, big R would be 1 minus x, and little r is 1 minus the square root of x. So the area of the washer is now pi times big R squared minus pi times little r squared. And for this problem, since we are simply asked to sit up but do not evaluate, I'm not going to simplify this. I'm going to leave it in its current form. But note, if we did want to evaluate, we would of course algebraically expand this as much as possible and most likely pull the pi out before evaluating. And as I had mentioned previously, it is perfectly reasonable to have a problem where we ask you to sit up an integral. So we would get it to this point and we would simply stop. But I will note that if you would like to get some extra practice, that is never a bad thing. So I'll just go ahead and let you know that when you do evaluate this for extra practice, you would get back pi. Let's go ahead and take this example and modify it slightly. Let's use the same exact region, but let's now rotate it about a vertical line. So as claimed, we're going to consider the same region, but now we're going to look at the solid of revolution formed by rotating about the line x equals 1. So let's go ahead and just draw the picture that we had previously. Y equals x. Y equals square root x. And we would like to form a solid by revolving this around the line x equals 1. So let's first kind of think roughly what that would look like. So we have this region from above. We're really just kind of cutting and pasting it over. And we would like to form this solid by rotating about this vertical line x equals 1. So we're going to take the mirror image over this line. And then we need to think about kind of adding depth. And I'm not going to try to be any more specific than this. So note that point of intersection of the two curves is still 1, 1. Now the key thing we want to observe is that when we now rotate around a vertical line, there's a fundamental difference in how we're viewing this solid. Instead of having a washer that we think of in terms of the area depending upon an x value, we are going to have a washer where we think of the area as depending upon a y value. That is to say, if we now choose a value of y between 0 and 1 and consider this small horizontal line segment I've drawn, when we rotate that line segment about the line y equals 1, what we will do is form a washer. So when we are using this washer method and rotating about a vertical line, we will have to consider things in terms of functions of y. So in this case, the volume will be the definite integral from 0 to 1, how the y values are varying, a of y. So we need to come up with a generic formula representing the area of the washer at y. So let's go ahead and just sketch that washer and do a bit of algebraic work to find a formula representing its area. So we do have this typical washer. We have to think about the small radius and the big radius. And in this case, we can see the big radius and small radius in our picture. The big radius is going to be the distance that furthest away curve is from the line x equals 1. The small radius is going to be the distance the closer curve is away from the line we're rotating about, x equals 1. And note, we want to have little r and big R both in terms of y. So in this case, we can just note to the side, big R is 1 minus, and if y is the square root of x, x is y squared. Little r is 1 minus y. So the area of our washer, A of y, is going to be pi times big R squared minus pi times little r squared. And because we are going to evaluate the integral, I want to go ahead and simplify this first algebraically. So if we pull the pi out, which is common to each term, we have 1 minus y squared quantity squared. So y to the 4th minus 2y squared plus 1. And we're subtracting away 1 minus y quantity squared. Y squared minus 2y plus 1. So now plus 1 minus 1 cancels. And then we're left with the following terms in descending order. Y to the 4th minus 3y squared plus 2y. And be careful of doing things such as distributing this minus sign. So the volume of this solid is given by the definite integral from 0 to 1 of pi, which we will pull out front, times y to the 4th minus 3y squared plus 2y. And note, getting it to this point, what we would consider the sit-up of the problem, is certainly where the most difficulty is involved. Once we have this definite integral set up, it becomes a matter of hopefully a familiar, more efficient problem, evaluating this definite integral. The process that we are using to set up this definite integral, though, is very typical. We want to sketch the region, think about what that solid would look like so that we can determine the shape of a generic washer. Because we're rotating around this vertical line, we're really going to have to put everything in terms of functions of y when we are using this washer method. So let's go ahead and evaluate anti-differentiating term by term. We have 1/5 y to the 5th minus 3 over 3 y cubed plus 2 over 2 y squared from 1 to 0. So we replace each y with a 1. And we subtract away what we get when we substitute in y equals 0. So in this case, the volume of the solid would be pi over 5. And this finishes up our current discussion, but of course, like any other topic, and maybe even more so in this case, it is very important to practice examples. And this would be an ideal time to go through some suggested problems in the book and really focus in on the process and understanding how we set up the definite integral to evaluate this volume and how we find the area of one of these generic washers. And also make sure you understand the process of sketching the region and the washer itself. That is an essential part of this process. So stay tuned and take care.